In this work, we focus on the few-shot image recognition task, where only one or a few labeled images are available for a new class, and meanwhile a large labeled base dataset is used for meta-training or pre-training. Since the support images are very limited for a new class, the obtained image features are not good enough to represent the class. To address this problem, we propose to use text data to provide addition information, where text features extracted by a pre-trained text encoder are regarded as semantic prompt to improve the visual feature extraction. In experiments, we evaluate 3 different text encoders for semantic prompt. They all achieve consistent improvements compared with the pre-training baseline on 4 datasets. In this slide, I will explain the motivation of our method. Given only one support image, the obtained image features may contain much noises. For example, given a support image of unicycle, the obtained image features may contain the features of the wall, persons, or the helmet of the rider, and fail to represent the class of unicycle. In contrast, the class name has rich semantic information about a new class, which can be extracted by a pre-trained text encoder and is very useful for few-shot learning. In this work, we propose to use semantic features as prompts to improve the visual feature extraction, such that the obtained image features contain the intrinsic features of the new class rather than spurious noises. To this end, we first feed image patches into a vision transformer. Then, the class name is wrapped with a sentence template and fed into a text encoder to obtain a semantic prompt. The semantic prompt and patches features are fed into the remaining transformer layers, where they are interacted via the spatial and the channel interaction modules. In this way, the semantic prompt can dynamically adapt the visual features to focus on the intrinsic features of the new class. Finally, we train the model via a meta-learning paradigm. Specifically, we first obtain a class prototype for each new class via averaging all support features of a class. Then, the classification loss of query samples is used to train the vision transformer and the semantic projector. We adopt 2 interaction mechanisms, which are complementary for each other. For spatial interaction, we first concatenate the prompt and the patch token sequence. Then, they are fed into a multi-head self-attention module, where the semantic prompt can pass semantic information to related patch tokens. For channel interaction, we first average all patch tokens to obtain a visual context vector. The visual context and the semantic prompt are concatenated together and fed into a MLP. The obtained bias vector is added to each patch token to adjust visual features along the channel dimension. In experiments, we evaluate 3 different text encoders for semantic prompt, including clip, SentenceBERT, and glove. Compared with the pre-training baseline, using semantic prompt improves the one-shot accuracy by 6.4% on the mini-ImageNet and the tiered ImageNet datasets. CVPR and FC100 have much lower image resolutions. On these 2 datasets, using semantic prompt also improves one-shot accuracy by 3.8%. In the Table 3, we can see that using the spatial interaction alone improves one-shot learning accuracy by 5.9%, and using the channel interaction alone improves one-shot learning accuracy by 5.4%. When combining them together, the one-shot learning accuracy can be improved by 6.9%, indicating that these 2 interaction methods can be complementary to each other. In the Figure 4, we can see that the model can focus on different regions according to the given prompt. For example, when prompting with Harvestman, the model pays more attention to the Harvestman spider. While when prompting with spider web, the model changes its focus to the spider web. In the Figure 3, we investigate how the selection of layers to insert prompts influences the performance, where different curves represent different layers to insert prompts. On these 2 datasets, we can that inserting semantic prompts to higher transformer layers usually improves the performance, while inserting semantic prompts to lower layers leads to performance drop. It may be because in lower layers, the feature extractor obtains much more features about low-level visual features, which have weak relationships to class semantics. While in higher layers, the obtained image features are strongly related to class semantics. Therefore, inserting semantic prompts to higher layers obtains better performance. In the Figure 5, we visualize the feature distribution using TSNE. For novel classes, it can be seen that using semantic prompt significantly improves the discrimination ability of few-shot image features. In summary, we investigate how to use text data to improve the visual feature extraction for few-shot learning. To this end, we propose a new semantic prompt approach, where text features are used as prompts to adaptively tune the visual features. Specifically, we propose two interaction mechanisms, which allow the semantic prompt and visual features to interact along the spatial and the channel dimensions. Finally, our approach is evaluated on 4 datasets with 3 different text encoders. Experimental results show that using semantic prompt can obtain much more performance gain than previous methods.